So we got to these problems here, and these are differential equations, but honestly you just solve them by integrating. In this class, solving a differential equation is basically integrating both sides, okay? So we did have a couple problems where you had to like separate the variables and stuff like that, but most of these problems, if you're trying to find what u is, or y, or whatever, you're just basically asking for the antiderivative. So the problem with this problem is the way it was written. It's too hard to integrate right now. So what we can do is rewrite this as basically 2 over x plus 1, x minus 1. And then we can assume that this is something over x plus 1 plus something over x minus 1. So we would assume that a rational function with x plus 1, x minus 1 as an LCD comes from the addition of two fractions, one with denominator x plus 1, one with denominator x minus 1. Okay, so we're going to try and figure out what a and b are, if you remember. So what you do is you recollapse this, multiplying here by x minus 1, like that, and top and bottom of the other one by x plus 1, like this. And this basically gives us ax minus a plus bx plus b all over x plus 1, x minus 1. So what am I doing? I separated it and now I put it back together again? What was the point of that? Well, the original function was 2 over x plus 1, x minus 1. And this new version of it is ax plus bx minus a plus b over x plus 1, x minus 1. So does anybody remember what we did to try to solve for a and b? We assumed that these would be equal, right? So if you look at the left side, you do not see any x terms. So you can write 0x here if you like. But that 0x on the left matches up with the ax plus bx. So you could just write 0x represents the ax plus bx. In other words, a plus b is 0. So hang on to that little guy, he's important. All right, and then also you can say that, see this 2 right here? That doesn't have any x's in it. And then here are some other things that have no x. This negative a plus b, there's no x there. So you can set this equal, you can assume that 2 is equal to negative a plus b. See? All right, so armed with these two little equations, you could easily calculate both a and b. Yes, question?
Can you explain the 0x plus 2 again?
Yeah, the original problem, numerator was just a 2, right? And then we wrote it in terms of a's and b's like this. So these two are still equal. And we can assume that the ax plus bx here should match the number of x's we have on the top over here. But there were no x's.
Okay.
So I assumed that there'd be like a 0x there. So that's why I wrote 0x plus 2, where it says 2 there. Okay, so now let's take these two equations. A plus b is 0, and negative a plus b is 2. And let's just add them together and see what we get. So we get 2b equals 2. What does this tell you? B is actually 1, right? And a is actually negative 1, because a and b are supposed to add up to 0. Okay, so we got this far, and what we're doing is basically rewriting the whole problem. So here's the original problem. It said du dx is equal to 2 over x squared minus 1. But we have since learned that this now means negative 1 over x plus 1 plus 1 over x minus 1. We actually decomposed this fraction into two much simpler fractions, both of which are very easy to integrate. Okay, so now it's time to integrate both sides. So if you just slap an integral on this side, don't forget the dx, and slap an integral on this side, dx, the left side is officially just u, right side is negative 1 ln x plus 1 plus ln x minus 1. So that says x minus 1 right there at the end. Sorry. Don't forget the plus c, and you don't have to write negative 1 if you don't want to. So it's basically ln of x minus 1 minus ln of x plus 1 in the end. We also mentioned, and I think Lauren was the one that figured it out, Lauren Train figured out that this can also be written as this. If you apply some rules of logarithms, you can actually put some of these logs together. So you can practice that. Once you get your answers, just look at the back of the book. Sometimes they leave them separated into multiple logs. Sometimes they make one log to rule them all. And put them together. Okay? Okay, either answer is fine, right? They're exactly the same thing. Let's go to the next one. This one's a lot harder. You can tell because the denominator is cubic, right? So, just going to need a little more space for that one. Can I erase the ink? Sorry, I was a little messy there. Okay. So I can get started without erasing, I suppose. So the first thing I notice is that dy dx is going to be x plus 1 over, and then this factors into x times x plus 3 times x minus 2. That's how you factor the denominator. You take out an x, and then it factors into x plus 3, x minus 2. Okay, so I believe that this is going to be a over x plus b over x plus 3 plus c over x minus 2. See? And then if you recollapse this, you get a times x plus 3 x minus 2 plus b times x minus 2 plus c times x plus 3 all over x plus 3 x minus 2. So that's ugly stuff, but that's what we've got. Okay, so you look over here and you say, okay, that garbage is supposed to represent x plus 1. Right, all that garbage on top. So let's look at all the different x squareds that are involved here. Let me erase some of this old ink here. Give myself some more room. Uh-huh.
Can you go over how you got the top?
Oh, how did I collapse that again?
Yeah.
Okay, you know like when you're adding 1/4 plus 1/5 plus 1/7?
Yeah.
You would actually multiply this thing top and bottom by 5 and 7. And you would multiply this one top and bottom by 4 and 7. And you'd multiply this one by 4 and 5.
Yeah.
That way you have 5 times 4 times 7 for every denominator. That's exactly what I did here. So I multiplied the a, since there's an x on the bottom, I multiplied the a by the denominators of the b and c fraction. I multiplied the b by the fractions, the denominators of the a and c fractions, see? And I multiplied the c by the denominators of the a and b fractions. That's why I have a times x plus 3 x minus 2, b times x and x minus 2, and c is times x and x plus 3.
Okay.
So it's kind of awful, but we have some quadratic stuff. Like there's a lot of x squared junk going on. Okay, so let's take a look at that first. So I'm going to regroup this. In the first term, I see that we have an a x squared. See that? And my voice just cracked. That was pretty cool. For a 39-year-old. A x squared. Okay. And here we have a bx squared.
That's on video.
And here we have a cx squared. That's on video. Alright. So I think we have an ax squared, a bx squared, and a cx squared going on here. Okay, those are your x squared terms. And then you also have, if you FOIL it out, you're going to have a minus x, or I'm sorry, plus x term, and there's an a there. So there's an ax guy there, and here we're going to properly. So for x garbage, we have basically a minus 2b plus 3c. Erase that, make it a little bit neater. Plus 3c. Those are just x terms. I'm too lazy to FOIL, so I'm kind of doing it in my head. And then there's some non-x garbage too. There's a minus 2a. I think that's it. Actually, I should say it's a minus 6a. There's a minus 6a. It comes from the first FOIL there. And that's actually the only term that has no x in it. Okay, so somehow this is magically supposed to equal x plus 1, see? So let's think of x plus 1 as 0x squared plus x plus 1. Okay? So can you tell me what a plus b plus c is?
0.
0, correct. Can you tell me what a minus 2b plus 3c is? It should be whatever's in front of the x here. 1, right. And then here is your non-x garbage, right? 1. And that should equal this non-x garbage here. So we can see that negative 6a is just 1. A minus 2b plus 3c is also 1. And a plus b plus c is 0. Okay, so let's write that down. I'm going to need a little space up here. So I believe that a plus b plus c is 0. I believe that a minus 2b plus 3c is 1. And negative 6a is 1. Out of those three, the one I like best is the third one, because it just tells me that a is negative 1/6. If you take the time to plug this back in to these two equations, you'll be able to pretty easily find b and c. And b turns out to equal negative 2/15. And c turns out to equal 3/10. Okay, 3/10. I'm not going to show those steps just because there's a lot of space, but you would basically plug in negative 1/6 for each a, and then you would have two equations and two unknowns. You have to eliminate c or something. So, okay. So what does this mean for us? Here's what it means. It means that, can I erase some of this stuff? Okay. That horrible function they gave us is very hard to integrate until we rewrite it. So we now believe that dy dx can be written as negative 1/6 times 1 over x. Or you could think of it as negative 1/6 over x. Let's do that. It's basically negative 1/6 over x plus negative 2/15 over x plus 3 and 3/10 over x minus 2. And that's not hard to integrate. That is not hard to integrate at all. The answer is actually right here. When you integrate this little 1 over x, you're going to get just ln x. When you integrate the 1 over x plus 3, you're going to get ln of x plus 3. And when you integrate the over x minus 2 term, you're going to get ln x minus 2. You just integrate one at a time. That's ln x plus 3, ln x minus 2. The tops of those are just your coefficients. And then answer.
So when you integrated them, you just factored all the tops out?
Yeah, you could just think of this as negative 1/6 and then times 1 over x. The antiderivative of that is negative 1/6 ln x. See?
Yeah.
And the next one you could think of as negative 2/15 times 1 over x minus x plus 3. So this is just minus 2/15 ln x plus 3, and so forth. And then you can think of this as 3/10 times 1 over x minus 2, which is just 3/10 ln x minus 2. Don't forget the absolute values whenever you integrate something 1 over something linear. And don't forget the plus c at the end. It's pretty awful, but it's harder than any question you see on the AP test. I'm just trying to show you the basic method. Okay? All right.